Okay, so here we are. So section 1.5.5 on loss functions for regression. So far we've been talking about the classification setting, and that's where you're mapping your input, whatever your predictor is, an image, some financial information, whatever, to a discrete class. So that could be, for example, whether the image contains a stop sign, or whether that X-ray data indicates cancer or not, or whether that financial data is going to tell you whether the stock goes up or stays kind of where it is or goes down. So always mapping from your data, whatever it is, into discrete classes. That's what makes it kind of a classification problem. So now we're just going to talk about the setting of regression, where that output variable is going to be continuous based, because it's going to be real valued. Almost always it'll be real valued. And so what do we do in that setting? So what's the right notion of loss there? So we're going to kind of discuss that in this section. We'll discuss the most common notion of the loss, which is the squared loss. You'll see what that is. And then at the very end, we'll talk about a couple of other possibilities. And I'm sure that later on in the book, as we use these concepts, you'll see other ones come up as well. Yeah, so I think so. Let's get going. So we'll do kind of a couple of the simpler calculations here as we go. There will be a location in the as we progress where I think his solution is kind of slightly more complicated than it needs to be. So I'll show you mine. But otherwise, it's going to be a pretty simple section. It'll kind of follow the previous one on classification. Okay, so let's get started. So here is the laser pointer. Okay, so let's talk about what the setting we're in. So we're talking about regression problems. So curve fitting, for example. Again, data to, let's say, temperature readings, and you have some predictors. What's the temperature going to be? And the game is going to be producing an estimate y of x of the value of t for each input x. So again, this is going to be, for example, the temperature, or the value of the stock the next day. And this could be the data this is going to be the data that you're going to be using. And so you at this point, you have essentially two pieces of information as before. So, and I guess you're already here. So you've got your uncertainty that's going to be quantified with this probability distribution, which is over x and t. So t is t is your target, x is your predictors. And notice now we're doing integrals because t is going to be continuous, and it's single valued, it's single dimensional, one dimensional. This procedure that we're going to discuss, you can easily extend to multiple dimensions, but for what we're going to be doing here, everything is going to be one dimensional. So we have an integral over a one-dimensional variable t, which is our target, and our predictor. So that's p of x. And then we also have some notion of loss. So what is the penalty you incur for assigning the value y of x when the true value was t? And so as before, we don't know the true value of t, so we've quantified it inside this probability distribution. So the thing we care about is the expected value of the loss. That's what this is. So essentially, you're taking the loss, which is this, and you're averaging it over the joint distribution of predictors and targets. And you can see that the loss has two components. It has the target and your predictor. And now the question is, what kind of a loss should you use? And in many settings, there are, the actual problem kind of motivates a loss to use. But if it doesn't, a really good one for kind of mathematical convenience, and it often gives really simple closed form answers that are actually very kind of meaningful, is the squared loss. And so it's called squared loss because the form it takes is, this is just the square of the difference between your prediction and the true value. So there's the two there. So now your expected loss becomes, your probability remains as before. You're still averaging just like you were, but now you actually plug in the squared loss. And now the thing we have to do is now figure out how to determine y of x to minimize this thing. So how are we going to do that? So this is kind of the first point where I'm going to diverge from what he does. So he suggests, because y of x is actually it's a function null, right? So you've got some continuous you got some continuous values x, and you want to assign a function for each value of x. So that's that's in general can be kind of quite complicated. It's a function mapping some high dimensional object, potentially infinite dimensional object, to a single value. So that's if x is finite dimensional, that'll be, you know, a function of multiple variables. In general, it could be mapping, you know, x could be kind of infinite dimensional, in which case this might be a functional. And he's going to use kind of the calculus of variations to solve this, but I don't think we need to use the calculus of variations, because we can do exactly what we did before of solving this problem for each value of x. So at each value of x, y of x is just a single point. So we're going to, what I'm going to show you now is just how to solve this at each value of x independently, and our function then becomes essentially the collection of those values of y of x. So let's do that. So we're going to go over here. So let's make sure you can see what I'm writing. So here's, oops. Okay, so here is our expected value of the loss, and we had it was equal to going to be y of x minus t squared times p of x and t dx dt. Okay, so what we want to do is we actually want to write this as some integral. We want to essentially be taking some integral over x, and then we'll be able to then minimize the thing that's being integrated at each point. So let's do that. So first we're going to write this as, so the loss is exactly as before. So now let's use, I guess it's the product rule. So this is going to be p of t of x, p of x. And now let's do dt first, and then d of x on the outside. Okay, so now you should see, like, look, this bit looks like something that we can just integrate. Sorry, actually, this whole thing is something that we're integrating against x, so we should be able to just minimize that. So let's just write that properly one more time. So now I'm going to, so here's our d of x, and then we've got inside the brackets, we've got p of x times y of x minus t squared p t of x dt. And so so basically we now have this function here that we can just, and let me switch colors so that we can just minimize this thing. We can minimize, it's going to be a positive value, right? So it's kind of p of x, all of these numbers are positive, and we can just minimize it for each value of x, and that will give us our value y of x. And notice that so let's just write that down here. So we're going to, so now we're going to have a minimization problem. So let's say y of x is going to be equal to like min over just a scalar value y of, you know, sorry, and that should be not the actual value, it's going to be, you know, arg min. So the value y that we're going to actually get of y of, and let's get rid of this. So y is now just, again, it's just some scalar. Squared p of t of x dt. Okay, now notice that this is an integral over t, so p of x we can just ignore, we can just remove it, because it doesn't depend on t, so it'll just be sitting outside. So let's just erase that. So there, that disappears, and now we just want to minimize this as a function of y, and that's easy enough. So let's just compute the derivative. So we'll just say you know, dy of dt, and now we're just taking the derivative of y, so we can just bring it inside. So there is y minus t squared dy pt given x dt. And so now this is just going to be equal to 2 times y minus t pt of x dt, right? So we just took the derivative of this thing with respect to y, and none of these other terms had y in them. So this is what we have, and we want to set this to equal to 0 to minimize it, or at least to extremize it, and it will turn out that actually is a minimum. Okay, so if we're doing that, then so that will disappear. So now we just have two. Oh, sorry, let me change colors here. Okay, so now we just have two equations. So we've got y minus t, pt of x dt is equal to 0. So let's just split it up. So this is the same as saying y pt given x dt is equal to t pt given x dt, right? So I just split up this. So this and this come over here, and this I move to the other side, and they're here. Okay, so now things just really simplify, because so y is not a function of t, so I can just move it outside. So we just get y pt given x dt is equal to, and this, what is this? Well, this is just the expectation of t under the conditional distribution. So we get, this is just, and we'll see this, I'll just write this as t of x. Okay, so that's on the right hand side. What is this? Well, this is just, we're integrating the posterior on t given x just over t. So this will just be equal to 1. So our final answer is y equals, so our y of x is equal to the expectation t given x. And that's it. So you don't need any calculus of variations for this. You just do it, you just optimize it pointwise, and you get the expression that we're after. Does he have it here? Let's just, yeah, this is exactly what he's got. So we just extremize this pointwise, and we get the answer that we're after. And the picture of it, so there's a nice picture of what it actually looks like. So let's focus on that for a bit. So here's the point xo that you're interested in, making an estimate for. You want your regression function, and now you have some uncertainty on the value of t given xo. So that's what this curve is. And so what we just found out is that your to minimize your squared error, the value that you should assign for xo is y, this y of x naught, which is the mean, it's the posterior mean. So the mean distribution on this is the t-axis, the mean distribution is here, and that's the value assigned for x0. And now you can see we haven't had any conditions on y of x being differentiable, smooth, whatever. So we can essentially just play this game exactly the same way at every point independently. We have a bunch of independent games that we play for each value of x, and that's essentially what we've done. So we don't need to. I think his method of the calculus of variations essentially is about finding this function kind of all at once. We can, in our case, we can actually just find it pointwise and then assemble those solutions. So anyway, so that's kind of what the situation looks like. Okay, so that's good, and let's continue. So this conditional average condition of t condition on x, this is called the regression function. I haven't heard that terminology, but fair enough, that's what it's called. And here he's just saying that we can extend it to multiple target variables. So this is, in that setting we have a vector t, and it's kind of easy enough to do that. So, and I think probably later on in the book we'll see that done, but you should be able to do it yourself given what I've just showed you for a vector variable. And in that case, you'll still get the same solution. So it's always the posterior. For this loss, it's always the posterior mean. Okay, so now the next little bit is quite interesting because, so we just kind of saw what the answer was, but we can actually approach the solution in kind of a slightly different way and kind of get some insight into the problem. And I thought that was actually quite cool. Okay, so what we're going to do is we're going to do this trick of adding and subtracting. So here was our loss, which is y of x minus t. That was a squared loss. And now what we're going to do, let's zoom in a bit, is we're going to, because we just found out that the solution is this posterior mean. So let's add and subtract that. So we haven't changed the loss. We just subtract e of t of x, and then we add e of t of x, and we square it. And now we get, but the cool thing is now we get we get some new terms. So we get one term which is a difference between our regression function and the posterior mean, so that's squared. And then we get another term over here, which is the difference between the posterior mean and t squared. So that looks like, it's kind of the component of a variance. And now we get these cross terms. And we're going to be integrating this over t. We actually have to integrate over t and and x, but we're going to first integrate. We could just like we did in the procedure that I just showed you. We can integrate against t first, and then integrate it against x. So let's do that, and then what'll end up happening is that these terms will essentially just disappear. So let's try doing that, and I'll just do it up here just to make it simple enough. Okay, so the first thing to remember is that these expectations are over distributions on t, so they're actually functions of x. So this is a function of x, this is a function of x, so t doesn't appear in them. So if we're integrating over, p of t given x, well, we can treat these as constants. So let's just do that. So let's try the first term. Let's try integrating y against y of x against, so this is going to be this first term, e t of x, p t given x. So that thing, well, as I just said, this term, and this term are functions of they're functions of x. They're not functions of t. So when we integrate against dt, it's just going to be y and e. I'll just write it that way. Okay. So that gives us that'll contribute a y and an e. Okay. Well, what is that product if we integrate it? Neither of them are functions of t. So that'll just give us a minus e squared term. Okay, so that takes care of that. Now what about y and minus t? So now t is of course a function of t. So that's going to actually contribute something meaningful. So let's do that. So that's going to be y. I'll drop the y of x times t p t given x dt. The y goes on the outside, and we can just write this as e of t given x. Okay, so times y. So we get a ye term here as well, and there's a minus sign contributed. So this whole thing, this is going to give us a minus y of e. And we have just one other term missing, which is going to be this expectation of t of x. Is that the one missing? Oh, sorry, that's the ye. Sorry, yeah, that's going to be the expectation of t of x times minus t. So let's do that one. And you can just see easily that is going to be, so if we integrate it, it's going to be the expectation times t times p of t given x. This goes on the outside, so this is just going to be an e squared. And so, and the minuses, that minus and that minus are going to cancel. So this last term is going to contribute an e squared. So now, looks like a bit of a mess, but that's going to cancel this, and this ye is going to cancel that ye, and so this whole thing is going to integrate to 0. So after we've done all of that, we see that all that remains is this contribution and this contribution that then we have to just integrate against p of x dx, because we integrated against p of t given x and we still have the p of x left, so we just integrate against that whatever is left over, and we end up getting this really interesting expression for the loss, which is a kind of a decomposition. It's very much like an analysis of the variance if you're familiar with ANOVA. It says that the expected loss you're going to get is going to have two components. There's going to be one component that's the difference between your regression function and the posterior mean, so the squared difference. And there's another component which is the difference between the the posterior mean and the target. And now what's interesting about that is that your regressor only shows up in this term. So this term is just essentially, this term is a noise term. It's kind of some amount of loss that you have to incur because t has some intrinsic variability to it, right? Like there's just given the value of x, t is just going to have some uncertainty around it that you can't really you can't capture with just a single point. So there's going to be some minimum amount of loss that you have to incur. You can call it noise, and that's this term. You can't do anything about that, but this term you can do something about this term. You can just set y of x to e of t of x, and reduce that component to 0. So this decomposition is actually really useful can be actually very insightful. So we had one method where we just kind of turned the crank and we did our calculus, and we figured out, okay, here's the answer. But kind of doing these kinds of decompositions can be useful because it can really give you some insight into the problem. Like we didn't have this insight about this decomposition into noise and a difference between our regressor and kind of the posterior mean, and now we do. So and now we can, for example, use this to, I don't know, you can, for example, measure the loss that you're getting and compare it to the minimum loss that you can possibly get, and kind of have some measure of the quality of your fit or something like this. Let's say you, for whatever reason, you couldn't set your regressor to be the posterior mean. You could measure how well you're doing by comparing to this kind of irreducible amount of error that you have to incur just due to the randomness in the system. So yeah, that's pretty cool. So and that's kind of what he talks about here. So the y of x returns only in the first term, exactly there, and it's minimized when y of x is equal to e of t of x. So that's what we do. The second term is the variance of the distribution of t. So this is, exactly, so this is t minus its, so the distribution of t given the value of x. So this is t, and this is its mean. So this thing is kind of the variance of t. We actually saw it. It's kind of like this variance, basically. And you can see that you can't actually, like the best you can do is essentially put your point in the middle of it, and then you will incur this loss because given your value of xo, t is not going to be always sitting here. It's going to be, it's going to be distributed around that point. And if you want to kind of summarize all that with a single point, well, then you're going to incur some loss just due to the fact that t kind of wiggles around that mean value. So that's what that's about. And yeah, this term represents the intrinsic variability of the target data and can be regarded as noise. And it's independent of y of x. It represents the irreducible minimum value of the loss function. So that's kind of what we just mentioned, that it's about, it gives you kind of a lower bound on how well you can do. So that's basically how you impose a loss function, a squared loss function, and then how you optimize it to figure out your regression function. So now the question is, well, how do we make decisions with that? And the approaches that he discusses, they go along the same lines as we talked about in classification. So remember, there's three approaches. Like you could either you could first determine the joint density. The joint density of p of x and t, and then figure out, and that was great because you could then sample from it. But for what we care about, decision theory, all you need is this posterior t, and then you marginalize, and then you figure out what the expected value of t is under that to get your conditional mean, and then make decisions based on that. You could find just p of t of x directly, and then come do your decision theory stuff after that, or you could just find a regression function and forget the probabilities. And why each of those approaches is good or not good, we already discussed in the previous section. So you can go and look at the video for 1.5.4 for classification, and it's the same discussion. So we're not going to go much into it. The final point here, and I think is actually useful, really useful to mention, is that of course, so the squared loss isn't the only possible choice, obviously, but there are actually situations where it can give you really bad results. And one of those ones is when the conditional distribution is multimodal. So when it has like multiple peaks. So how do you pick? Sometimes the posterior mean can actually fall in between the peaks. So like let's have an example of that. So let's say you had, let's say this is this is t, and let's make this is the posterior of t given x. Okay, like suppose you had something like this, right? So you would kind of pick your posterior mean to be here, but that would kind of correspond to a value that actually doesn't occur very much, and so that can sometimes give you bad results. So despite the fact that it might kind of minimize your squared error, it might not be what you necessarily want to do. So there are kind of other solutions to this. He's going to kind of capture a bunch of them under this rubric of the Minkowski loss. And so the main idea there is you just take the absolute value and you raise it to the power of q. Instead of, so we've been talking about a squared loss for which q is equal to 2. But there are other possibilities, and actually a couple of cool ones to talk about. And I think there's some exercises about this, but it's actually fun to work it out yourself. Is So we already figured out, what the regression function is when q is 2, so when we're using a squared loss. But if you use q equals 1, and that looks like, actually there's a picture of it. So this is what the loss function looks like when q equals 1. You see it just kind of goes up. It's kind of the absolute value kind of thing. We've been using q equals 2. Here's what it looks like when q is less than 1. It starts kind of getting, non-convex. Here's q is equal to 10. So interestingly, and this is kind of a fun thing to work out, is that if you set q equals to 1, so you use that, that sharp one, then the actual answer becomes a conditional median. So if you've ever seen things like, median filtering or people using medians, it actually corresponds to different kinds of loss. And that loss is actually, one of the advantages is that it's more robust to outliers. So the squared loss, for example, if you have points that are quite far from the mean, they're going to contribute enormously, right? Because they get squared, their deviation gets squared. But maybe you want to be kind of robust to outliers, so you'll actually use an absolute value. And it turns out, despite that non-differentiability that it has, at its center, you can actually still figure out that the regression function, you can find it in closed form, and it is the conditional median. So that's kind of a cool result. And then if you set q smaller and smaller, so even below 1, then as q goes to 0, you get the conditional mode. So this becomes kind of the most likely value. And actually, this then starts connecting to the classification case. Remember, in that setting, when we were trying to minimize our misclassification loss, that's kind of the situation we were in, where we were essentially giving a loss of 0 if we got it exactly right, and then giving some constant loss when we got it wrong. And that's essentially what this function here tries to do. So let's let me pick a good color to draw it in. So as q goes towards 0, this function kind of starts looking a lot like, I don't know if it becomes even sharper and sharper. So it ends up becoming closer and closer to essentially that misclassification loss that we had. So it'd be kind of 0 over here, and then kind of, I don't know, like 1 everywhere else. And then what you end up trying to do is you try to assign your values to the most likely, to the point, to the highest point of the posterior, so to the most likely value given the posterior. And that's what we did in the classification setting, and that's what you'll end up doing in the regression setting as well. So there you end up assigning your values to what would be the posterior mode. So for example, I don't know if this peak was kind of slightly larger, you would assign it to that value. And that's with the kind of q of 0. So the cool thing about that, I just think it's cool because it allows you to kind of capture a few different settings and a few different notions of loss with just a single parameter. So I think it's a cool one to know about, and I think it's fun. It would be fun to, maybe this exercise, 1.27, solves it. Maybe that would be a fun one to try and to kind of drive these results. Okay, so I think that was about it. A pretty simple section talking about loss functions. So what we do, loss functions regression, when we have a regression problem that we're trying to solve, mapping our predictors to continuous values. And I hope you saw that it's, the procedure is still pretty straightforward, and you actually get some really nice answers. So if you're using the squared loss, it's usually your regression function is the posterior mean, and as we saw at the end, if you're using the absolute value, it's the posterior median, and as your q here goes to 0, as you start approaching the what they call the 0-1 loss, you approach the conditional mode. And there are other loss functions as well, but these are just some of the most common ones and easiest ones to work with. Very good. So I think that's about it for this section. And next time we're going to be starting a big section on information theory. So that'll be really exciting. So yeah, so thanks for hanging out. And if you like this video and you found it useful, just please press the like button. That'll help me out a lot. And yeah, that's it. See you next time.